Hello everyone, and welcome to the presentation of our paper with the topic Decision Support on the Shop Floor using Digital Twins. My name is Franz-Georg Listel, and together with my colleagues Jan Fischer, Roland Rosen, Annelies Sohr, Jan-Christoph Wehrstedt and Michael Weyrich, I want to present you on high-level architecture as well as functional components for simulation-based assistance on the shop floor. In the following, we will first motivate our approach, addressing challenges and our vision of a digital twin, before going into a bit more detail about the individual functional components. But let's start right away. The general goals in production are well known: reducing costs, increasing productivity, be more efficient and flexible. Maybe also their resilience is something new due to the COVID pandemic. At the same time, optimal production depends on many different things, as can also be seen in this picture in the middle, drawn by an 11-year-old kid, Tim Portzelt. There are various robots, machines, and many people in different application roles. For example, the workers at the machines, a shift supervisor, or also development engineers. Intelligent assist systems follow the idea to support these stakeholders of production system in their decisions, and can thus be useful applications for helping to master the various challenges. Some of the challenges, especially associated with the digital twin-based assistance, are presented here. For example, like forecasting, where one would predict future behavior to detect undesirable trends and finally prevent them. But also, of course, topics like optimizing of plant operation and replay of situations, where one would analyze situations reversely based on recorded values. In addition to that, we see also virtual sensors and offline reconfiguration planning based on the current plant state as important challenges for digital twin-based assistance on the shop floor. But how do we solve such problems? Here, our vision of a digital twin comes into play. First of all, our vision of a digital twin, of course, also refers to a virtual representation and a description of a component, product, system, infrastructure, or process. But what's above that is a bit shown here in the right picture. Below we see the real twin, and on top of that the digital twin. The digital twin consists of all relevant semantically linked digital artifacts. These artifacts are shown here in the right picture in these small white boxes. They can, for example, be descriptive and executable models, simulation models. They can include design and engineering data, operational data, but also behavioral descriptions. In addition, a digital twin exists and evolves along the whole life cycle of the real twin, and it is synchronized with it if it exists. In our opinion, on top of that, the combination of AI and simulation models will come more and more to the fore, facilitating more powerful applications by the combined use of these rigorous models. The decision support for the shop floor and its functional components that are presented in the following are a step towards this ambitious vision. But now let's start with an overview of the functional components. On the left side you can see the decision support system in the dotted rectangle and how it interacts with the physical world, mainly the environment, real assets or humans. In general, decision support systems are interactive computer-based systems which utilize data, models, knowledge and so on to support people who are required to solve complex problems. A decision support system for the shop floor specifies this definition. It integrates and connects production data, simulation and AI models to address the growing challenges. On the right side, the decision support system in the rectangle is enlarged and you can see the building blocks of the digital twin-based decision support, with the simulation as a central part. As described in our vision, a digital twin can contain different models, and the same is true for simulation models, of course, so that the decision support system can contain, for example, material flow models, process models, kinematic models, or any other simulation model. Besides that, data provision and data extraction, model execution and analytics, as well as knowledge base and application and user interaction are essential building blocks for our decision support system. On the next slides, we will go into more detail about these building blocks and explain their use and connection to each other. So let's start with our first building block. data provision and data extraction from heterogeneous IT systems. But what does that actually mean? So for Industry 4.0 technologies, usually a large amount of data is permanently collected by various sensors, connected machines, systems, and digital models. But due to the evolutionary development of most of the factories, the data landscape in production system is quite heterogeneous and comes from very different sources. For example, new machines and new technologies are permanently integrated into the legacy systems or existing structures of the production system. Some of these data sources and data formats can be seen, for example, on the left side. For example, ERP systems, SCADA, and Excel. But also, of course, as data structures, XML and JSON and so on. But decision support system, they need these data to provide the user with analytical components to make decisions in different situations. For this, the data needs to be extracted, cleaned, and mined from the systems on the left side, so that they can be consumed, for example, by further services, machines, or users. Several data services already exist for this purpose, which can be used, and which we are also using. But still, data connectors to existing data providers need to be set up, as well as the mapping between the proprietary data models of existing IT system and standardized data models need to be simplified. The second building block is now the knowledge base, integrating the data just mentioned into semantic models to enable and empower analytical components such as machine learning algorithms, simulations, and optimizations algorithm. Here we focus explicitly on simulation. For that, the knowledge base should represent the knowledge in the production line and at the same time be a virtual representation of the production line itself, thus forming an ontology of the production domain. This can be seen here on the left side. We in particular are using knowledge graphs for this purpose. Within them, the use of different layers and application and decision support requires reusable, standardized, flexible, and extensible means for data exchange between them. In addition, simulation knowledge and simulation-specific data need to be included and extracted, which leads to the linkage of simulation components on the one hand to the data in the domain graph on the other hand. Thus, the knowledge of a simulation expert can be kind of formalized. This linkage can, for example, happen by simple triple matching and pattern development. After that, it's now rather easy to generate or parameterize executable simulation models from the graph models by scripting languages. We, for example, used Python for that purpose. And what you can see now here on this slide is more or less an implementation approach for this knowledge base, or better to say for the production domain part. Here we work together with a neighboring group of us, which is occupied with the structure of an ontology library, whose goal it is to make such a reuse possible by means of semantic models. The rough architecture is that starting at the bottom with a generic top-level ontology, which defines really generic concepts like objects or activities, for example, we go upwards and get more and more specific. That means, for example, in the middle, in the dark green boxes, we have industry-specific ontologies that can, for some use cases, be reused. But on top of that, we have really customized project-specific extensions for solutions with very limited reuse potential. And out of these data structures, as said, we want to create simulation models, which is now our next building block. The simulation models form the basis for the analytic algorithms and represent the current state of production at different levels. That means that depending on the task for decision support, there are different modeling options and level of details used. For example, within one production unit or for the entire production stage. In the context of factory simulation, the two main simulation types are material flow simulation and 3D kinematic simulation, which can be seen exemplarily on the right side. The lower picture is a material flow simulation and it models the logistics inside the production system. The upper picture is a 3D kinematic simulation, which is used to analyze the interaction within the production cells between machines like robots, humans, and the product. To deliver value to different stakeholders on the shop floor, these models need now to be executed and further analytics need to be added. Besides simulation and optimization, AI is increasingly coming to the fore. The target is to give us decision support in a descriptive, predictive, or prescriptive manner. And what now can be seen here is a figure that shows us an example of a concept for the implementation of prescriptive decision support. Here we want to evaluate upcoming decisions in a systematic way to end up with the best decisions in the field of the production planning and scheduling. The process starts by feeding the simulation and an abstract model by the input data. The abstract model is what in the end should be optimized to get for example, an optimized schedule. The output of the simulation, which could be, for example, scheduling scenarios, are also fed to the abstract model and at the same time fed to validation used as feedback for reinforcement learning. In the optimization part, the abstract model is now optimized, mathematical or by meta-heuristics like genetic algorithms or AND algorithms. The resulting schedules are proposed and can again be validated by the simulation. What we have here is then a concept for the combination of AI, optimization, and simulation models. It is a first approach in a European funded project assistant, which will be tested and implemented for 3 specific use cases. And before coming to a small summary, that's what I want to refer now a bit on this slide. As said, we have this European funded project, which is called Assistant, that is short for Learning and Robust Decision Support System for Agile Manufacturing Environments. Here the overall goal is more or less to combine simulation, optimization, and artificial intelligence for process planning, production planning, and scheduling, as well as real-time control in production systems. On the bottom right, you can see this 3 use cases I just mentioned in the slide before from Atlas Copco, Stellantis, as well as Siemens Energy, where we as Siemens are particularly focusing on production planning and scheduling for the Siemens Energy use case. But now let's come to a small summary. In this talk, we wanted to give you an insight into our vision of the digital twin and especially, of course, into the path to our vision, which is this decision support system for the shop floor. We gave you an introduction to the most important technological building blocks that we see and set up more or less the requirements and the connection between the building blocks or the functional components. The 2 topics that are in the foreground for us and especially in the European funded project are integration of knowledge base for simulation and production knowledge, as well as approaches for hybrid models on the shop floor. And on top of that, what we see as very important is that even incorporating autonomous systems, the human remain the decision makers and they should remain the decision makers, so that the goal is to support and help the humans in their decisions. And with these words, I'm also at the end of my presentation. So thank you all very much for your attention.